In this video, I wanted to discuss how do we evaluate trigonometric functions using degrees instead of radians, which I apologize that these have been a little bit out of order based on the packet, which has not been my intention, but it's just sort of working out that way. But I did forget to post a video with some examples on converting from degrees to radians, which was on your quiz from 4.2 or whatever. But you know, I did talk about the equivalence between degree definition and radian definitions, where radians are defined based on the unit circle, where one complete circle is based on the circumference, 2 pi. Whereas 360 degrees is an alternative definition which describes, well, how far does it take, an angular approach to, well, what does one full rotation mean in terms of degrees, where, the top is 90 degrees, which is, a right angle, which is defined to be, instead of being the distance t, like we've been defining trig functions, we're going to now talk about, well, what about the interior angle, which is what radians is. Radians is the associated distance to the angle. But anyways, 2 pi is the full circumference, 360 degrees is a full spin. Whereas half a spin is 180, a quarter of a spin, right angle is 90 degrees, and so on. But when we're looking at a filled-in unit circle, and we've been using it quite a bit, where is it? It's in one of these pages of the packet, like this one. It presents the position both in terms of degrees and radians. Like, for example, well, the first terminal point from the initial, pi over 6, could also be defined by 30 degrees. Pi over 4 is 45 degrees. But how do I know these are equal? But also another important thing to remember is if I know, like, the degree measurements are way easier to remember because most people are familiar with, well, the right angle is 90, halfway angle is 45 between 0 and 90, and 30 is the third of the way point to 90. Obviously, the reason degrees are so useful is it's way easier to understand the relationship between those, whereas the pi's, if your fractions are not your favorite thing, are a little bit harder to understand. But notice that pi over 2, exactly 1/3 of that is pi over 6. Not coincidentally, a third of 90 is 30. Anyways, going back to but to summarize, since 360 degrees was equal to 2 pi, that implies that 1 radian is, because that implies pi radians is 180 degrees, and so 1 degree is pi over 180, and 1 radian is 180 over pi. But if I have a measurement in radians, this is my, for in terms of dimensional analysis, if I want to know, well, what do I multiply by to convert from one unit into another, these were those key principles. And so say, for example, I wanted to know, well, what is pi over 6 in degrees? Well, we already know it's 30 because we could look at the unit circle, but the point is we could take that, directly multiply by 180 divided by pi, and that will convert it from, because originally it's in this unit, and I know that for each 1 radian, it should be equal to this many degrees. So if I just multiply that by that, that should do it properly. Notice the pi would cross cancel because it's on top and bottom, and then 180 divided by 6 is just 30 degrees, the proper fraction at that location. And you could do that with all points. If you know the radian measurement, you can go back and convert them to degrees. But also, if you find it hard to memorize all of the positions on the unit circle, it's way easier to memorize them in degrees. You can always convert them back to radians later. So say, for example, 120 degrees, since this one's 90, 120 should be the next one over because it's 30 past. If I forget, well, what is that in radians? Well, I personally have it memorized as 2 pi over 3. We could always just figure it out by multiplying by the reverse principle and performing dimensional analysis. So if I just take the degree measurement, multiply by pi over 180, that will revert it back to radians. And then what I would get is, well, 120 pi over 180. Sorry, it will not let me write for some reason. Let me move that. And then I could reduce this fraction because, well, each one is divisible by 10, which would reduce down to 12 over 18 pi. Often we just pull the pi outside like that. But you could write it on top or on the side, doesn't really matter. And then 12 over 18 would reduce by by 6, sorry, down to 2/3 pi, or 2 pi over 3 if you prefer. You know, tomato, tomato. Some people write it one versus the other way. And this would now be our measurement in radians. Another thing I wanted to mention, when you're working on your tests or and writing mathematics, it's very important that when you do something in degrees, you make sure to write the degree symbol. Because if I was to just write 30 as my answer, that's not the same as 30 degrees. 30 is not equal to 30 degrees. So anytime we're using a degree measurement, we must write that symbol on it, or else it is not correct. Now, it's sort of like the difference between 1 foot and 1 meter. 1 is not equal to 1. They're not the same. If I just write 1, say I'm trying to build a road that's 1 meter long, and I write 1, who's to know if it's in feet or meters, feet or meters? And I think you see what I'm saying. It's very important to denote your units, even in the mathematical sense, even if it's obviously in degrees. Like say I'm talking about a triangle who's got an angle of 30 degrees. You don't just write 30 when you're talking about angles. Now, that being said, if it's in radians, you don't necessarily have to write radians. Like notice how up here I wrote rad as a shorthand for radians, is what some people will often do. But radians is a unitless unit, which means that technically it's a direct unit of measurement. It's not like meters or feet, where it has a specific coded meaning to it. It's actually unitless, which just means it's a, you could write rad if you want, but typically we're not going to write radians because it's implied. If it's just a number, it's just a normal number when all is said and done. But summary, 120 degrees is equal to 2 pi over 3. And that's why when you're looking at the unit circle, you'll see them both next to each other because it's the same value. They're really equivalent. It's a convenience thing. When I'm looking at the filled in unit circle, I have all the special points on the unit circle, both in radian and degree mode, and I have their points, their terminal points. But that being said, now the main point of this video is how do we actually evaluate trigonometric functions using degrees, which really should have been in the last lecture, but that one was really long also. So right now I'm if you're wondering the organization, I'm just sort of talking about things that I missed, not on purpose, but are really important. Let's say I wanted to figure out, well, what's the cosine of 210? First, it's going to work exactly the same as before. Is I want to know, well, where am I at? Cosine will still return x. So if I'm looking at the unit circle, let me move to up here. 210 degrees is going to be slightly past 180. And a lot of people find it easier to think in terms of degrees, which is why I'm bringing all this up. Well, 180 is right here, and then 210 is going to be the next is 30 degrees past 180. 180 is exactly turning around. And then 210 would be right there. So that would be 210 degrees in terms of angle. And then the radian measurement is just going to be the actual physical distance, which is just going to be the value that's listed in pi, which if I didn't know what it was, I could always convert it. And you can even use a calculator. 210. Actually, I wouldn't use a calculator because that's not going to give it exactly. It's going to give you an approximation. But if I take that 210, multiply by pi over 180, that would give me exactly the value. And basically the problem is when I put that in my calculator, pi is a really weird number, so it's gonna give me a weird answer. But if we're gonna reduce it, that's probably what I would do. You could also just use, if you're not great with fractions, what you can do is use your fraction to reduce everything but the pi, 210 over 180, and then frac it to make it into a fraction. But that will give us 7 pi over 6 in radians. Or, really that would reduce by 30 because each one is divisible by 30. Yeah. 210 divided by 37 and 180 divided by 36. Cool. Anyways, nifty, neat. You can rederive each position on the unit circle by just remembering your conversion principles. Anyways, going back to what's the cosine of 210 degrees? That's going to be equal to the cosine of 7 pi over 6, because those are equal measurements. They're in different one's in degrees, one's in radians, but these are meaning the same thing. So if I'm trying to evaluate it, I could return to my unit circle approach, and well, cosine is just going to be the x location there. I didn't actually need to do any of that. So all of that math was totally not necessary, but it helps us to compare to what we did before. But cosine is going to be the x location there. That's going to be negative root 3 over 2. Again, you could look at your unit circle as well to double check that. But anyways, that's how we evaluate trigonometric functions in degrees. Or say I wanted to do the sine there. Sine is going to be the y coordinate at that location, which since it was in quadrant 3 was also negative, and it's the other part of that point. And tangent will still be the ratio of y to x, which at that point, sine is the y and cosine is the x. So tangent of that 210 will be equal to that ratio, which will again reduce because the negatives will cancel, the halves will cancel, and that will leave us with 1 over rad 3, which is root 3 over 3, or about 0.57. But anyways, notice we can get exact answers and figure this all out when still using degree mode. And if we're talking about coterminality, say for example we have a value which is outside of our normal range of 0 to 360, one circle, we could still, like before when I said you can find a coterminal answer by adding or subtracting 2 pi, in degree mode that would just change to 360 degrees. Because 360 would represent one full circle. And if we add that, we're going to be exactly in the same spot. It's just like doing one complete spin and pretend I'm spinning around in my chair and going back to exactly where it was before. So, like, say I wanted to solve what's the cosine of 870, what I would need to do is I could subtract 360. Oh, sorry, this is cotangent. Let's do the sine instead, but just because I'm trying to wrap this video up, it's becoming quite long as well. I'm trying to avoid that, but, oh no, this is cosine. I'm just, sorry, my tablet's off center. If I want to do the cosine of 870, that should be equal to the cosine. If I subtract 360 from that, that would leave me with 510. Because those are coterminal, those would be at the same terminal point. And then if I subtract 360 again, it will also be coterminal, which would be at 150. But I could continue cycling through equivalent positions until I find one that is on the unit circle. And then I could say, well, 150 on the unit circle, I know that that is over there. And so cosine is going to be the x coordinate. It's going to be that. Or, you know, we can then, once we know the position, that's all that matters. Then it's just a matter of, you know, well, is it cosine or sine or one of the others?